Welcome back. Our previous video looked at how factor models and learning models are related but different. And in today's video, we'll get specific about how agents actually update their beliefs while making some strong assumptions about the way in which they do that. And the most natural place to start for what we call belief updating is a framework called Bayesian updating. And the reason that it's a natural starting point is that it has basis in Bayes' rule, which is a very common mathematical and statistical framework used in a variety of different domains. And second, it gives nice, simple formulas for how beliefs are updated as signals are accumulated. And as with most mathematically elegant formulas that we've come across in this course, there are some desirable implications of making these assumptions, but there also are some undesirable implications, and we'll cover those as well. Another point in favor of Bayesian is that it's sort of the lingua franca of learning models, and so we can always benchmark whatever other learning model we want to impose against the Bayesian updating approach and use that to figure out if this other approach has merit. So let's go through the Bayesian updating of the new information that is contained in the signal S sub it. And as mentioned, the simplest way is to assume that the agents are updating in a Bayesian fashion. And as the name implies, and as I've mentioned, this comes from Bayes' rule. And the exact formulas are given here. I want to consider how the agent is updating their beliefs about the average and the variance of their AI. And the T+1 versions of these formulas are going to tell me what the agent believes the new value to be and how certain they are about that value. And as you can see, these are just weighted summations where the weights are the variance ratio or the inverse variance ratio, depending on how you define it. So if I have some belief E sub t, I'm going to weight my prior by the ratio of the noise to the total variance of the signal. And I'm going to weight the signal by how confident I am at time t in my belief about A and the total variance. So this is not exactly the variance ratio that I showed you in an earlier video. This is the current period belief of the uncertainty in my A sub I. So if I'm really uncertain about my belief, I'm going to give more weight to the signal. But as my certainty increases, then I'm going to give very little weight to the signal. So as my certainty increases, my variance is going to decrease. That's going to put less and less weight on the signal, and it's going to put more and more weight on my prior. So these are the Bayesian updating formulas, and we call the updated formulas the posterior beliefs, and the other formula, the period t subscripts, are the prior beliefs. So in period t, I have some prior beliefs, and then by the end of t, I have these posterior beliefs, and the posterior beliefs from period t would become the prior beliefs in period t+1. And then you just repeat accordingly. What are the properties of a Bayesian learning framework? Well, first is that the agent is never truly certain about their value of A. They can be very, 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 very little uncertain, but they can never be fully certain. Another property is that if there's some variance in A in the population, then as I accumulate signals, my uncertainty about my particular draw of A is going to go to 0. And in particular, it's never going to reach 0 because of the thing on point 1, but as I accumulate more signals, I'm going to become more and more certain of my value. And then as I get an infinite number of signals, then my certainty is going to converge to 0. It's never going to get there because of point 1 in a finite sequence of time. But if I could have an infinite number of signals, the variance would eventually go to exactly 0. And then, as I mentioned in an earlier video, the speed at which I learn is going to be dictated by what's called the signal-to-noise ratio. And so if I have a higher signal-to-noise ratio, then I'm going to learn much more quickly than if I don't. And so you might be thinking, well, these properties, they may not be desirable, but they come with a very mathematically convenient set of updating rules. and they are intrinsic to the Bayesian outlook on life and the world. And so those are maybe 2 points in favor of using it. But we got to start somewhere, and so starting with Bayesian might be a natural place to start. So we have this nice, convenient framework that gives us compact updating rules and a nice recursive formula for the belief updating. And we also saw that there are some mathematical properties associated with these that this framework imposes in terms of the speed of learning and the presence of uncertainty after so many time periods. And these are hardwired into Bayesianism. But Bayesian updating isn't the only way to update beliefs, and so we'll talk about some additional concepts that would apply to non-Bayesian updating. And we'll also introduce a Bayesian-based framework called the Kalman filter that is used in a variety of domains, even outside of economics. So I'll look forward to seeing you in that video.